Okay, let's get into this. We use these multimodal large language models, MLLMs, all the time now to understand, well, images and text together. But have you ever noticed when you ask about image details, they sometimes just miss things, really crucial things?
Oh, absolutely. They can tell you there's a dog, sure, but ask the breed or if, I don't know, the collar looks worn out, they often stumble.
Right, they get the big picture of the global stuff, but those fine-grained details.
Exactly. And that's what we're diving into today. There's this really interesting new paper on something called LLaVA-SP.
LLaVA-SP.
Okay. And it tackles that exact problem, getting better visual detail without the crazy high computational costs you usually see with, say, boosting resolution way up.
Got it. So let's set the stage. Why do these powerful models have this blind spot, this clip blindness, some people call it? Most of them use Clay-Cop PVT for the vision part, right?
Yeah, the vast majority lean on Sleek-Clay VIT as the vision encoder. And it's great for general recognition, but it has this known limitation, especially with local details and spatial relationships.
How things are arranged in the picture.
Precisely. Think about what the vision transformer, the VIT, has to do. It needs to take a 2D image, a picture, and turn it into a sequence, like a string of words, something 1D that the language model can actually process.
Ah, right, that flattening step. That's where things get lost.
That's a huge part of it. Imagine tearing a map into thin strips and feeding them in one by one.
Okay.
You've just totally messed up which cities are next to each other, haven't you? They might look far apart in your sequence, even if they were neighbors on the map.
Yeah, that makes sense. You lose all that next to each other information.
Exactly that. That disruption happens when you force 2D visual data into 1D patches for the LLM.
Okay, so the architecture itself causes problems. But the paper also mentioned another angle. LLaVA-SP addresses something about the training data.
That's the other key piece. These models are often initially trained on just massive amounts of image-text pairs scraped from the web. And, well, that data can be really noisy.
Noisy how?
Like, the captions might just say, a person walking. Super generic, right?
Okay.
If that's all the model sees, it never really learns to pay attention to or even describe the finer points, the style of their coat, the texture of the pavement, whatever. It learns the most common, basic description.
So it defaults to being vague because the input was vague.
Pretty much. And, we've seen people try to fix this detail problem before, haven't we?
Oh, yeah. Usually by just cranking things up. LLaVA 1.5 went to 336 resolution. I remember seeing intern VL pushing, 1024?
Huge resolutions. Or others try feeding in different parts of the image separately in parallel.
But anyone who's had to manage the budget for training these knows what that means. Costs go way up.
Way up. Crippling costs, really.
Yeah.
Every time you bump the resolution or add parallel streams, the number of visual tokens the language model has to chew on just explodes.
Right.
And that's not just training costs. It hits you, the user, too. Inference gets slower. The model takes longer to give you an answer.
So the big question LLaVA-SP is asking is, can we get those richer visual features, restore some of that lost spatial detail, without paying that massive token penalty?
That's the million-dollar question they tackled.
And the answer they came up with is kind of amazing. It boils down to adding 6 extra tokens. Is that right? 6 spatial visual tokens.
Just 6. It sounds almost too simple after all those efforts with massive resolution increases, doesn't it?
It really does. How do they pack so much punch into only 6 tokens?
Well, that's the clever part. It's all about the architecture. They don't actually increase the total number of visual tokens the main language model sees by much. Instead, they make those 6 new tokens incredibly information dense.
Okay. Oh.
The magic happens in the projector. That's the bit that connects the vision part to the language part. In LLaVA-SP, this projector gets 2 new key components.
Right. Component 1.
First is the spatial feature extractor, or SFE. This is what actually generates those 6 new spatial tokens. It looks at the original features coming out of the VIT and processes them using, interestingly, convolutional kernels.
Convolution.
Yeah.
Not transformers.
Uh-huh.
Okay, interesting. And the second component?
That's the detail feature integrator, the DFI.
Yeah.
So imagine the 6 SFE tokens are like headlines summarizing the image's spatial layout. The DFI then acts like a fact checker with a magnifying glass.
Oh, okay.
It uses cross-attention to look back at all the original fine-grained detail from the VT's feature maps, and then intelligently fuses that high-res information into those 6 existing spatial tokens.
Ah, I see. So the SFE creates the spatial slots, and the DFI fills them with rich detail pulled from the original high-res features. It's like a smart compression.
Exactly. You get the spatial structure and the fine detail without overwhelming the LLM.
You mentioned convolution for the SFE. That feels a bit old school in the age of transformers. Why did they go that route? Did the ablation study show it was better?
They did, yeah. It's a great reminder that sometimes the best tool isn't the newest one. The experiments showed convolution just worked better for this specific job.
Why, though?
Because convolution, by its nature, is really good at looking at local neighborhoods in an image. Those sliding kernels are designed to pick up on spatial patterns and relationships between adjacent pixels or patches.
Right, they're inherently local processors.
Exactly. Whereas trying to make a big transformer block, which naturally wants to look everywhere, global attention, focus intensely on just local stuff, it's just not as efficient or effective for this task. The convolution-based SFE gave them much better results on capturing that fine-grained spatial structure.
Makes sense. Use the right tool for the job. Okay, so we have these 6 information-packed tokens, but LLaVA-SP doesn't just use them one way. There are 2 versions, right? Cropping and pooling.
Correct. They realized different visual tasks might benefit from emphasizing different kinds of information. So these 2 variants tweak how the SFE initially gathers the information before the DFI enriches it.
Okay, let's break them down. LLaVA-SP cropping first.
Think of LLaVA-SP cropping as the zoom lens. It's designed for detail. The SFE progressively crops inward on the VIT features, focusing on the central region first, so it builds its understanding from the center out.
I see.
This makes it really good for tasks where you need to pinpoint something specific, like locating an object precisely or understanding very fine details in a small area. Visual grounding tasks.
Got it. Like finding a specific landmark in a busy photo. So if cropping is the zoom, what's pooling?
LLaVA-SP pooling is more like the wide-angle lens. It aims to capture the global semantics, the overall picture first. It uses adaptive average pooling to create features at different scales, arranged more from abstract to specific.
How we normally look at things, maybe. Glance, then focus.
Kind of, yeah. It's inspired by that hierarchical perception idea. So this version tends to be better for general visual Q&A, where you need to understand the whole scene context.
And the results back this up. I remember seeing something about the cropping version excelling at specific tasks.
Absolutely. In things like the RefCoco benchmark, which is all about precisely locating things based on text descriptions, LLaVA-SP cropping came out on top. It really showed its strength in fine-grained localization.
That's clear evidence for the design choice. But looking broadly, how did LLaVA-SP perform overall compared to, say, the LLaVA 1.5 baseline?
The improvements were pretty striking. When fine-tuned using LoRa, LLaVA-SP beat LLaVA 1.5 on 10 out of 11 standard multimodal benchmarks.
Wow, 10 out of 11. Any specific numbers that stand out?
Yeah, some solid gains. On VQA V2, it was up by plus 0.8%. VizWiz, which uses really challenging real-world images from visually impaired users, saw a big jump of plus 5.9%. And TextVQA, understanding text within images, went up by plus 2.5%.
Those are pretty meaningful improvements on established benchmarks, but the killer feature, the one that got my eye, was the efficiency claim. They got these gains without slowing things down.
That's the crucial part, and it really validates the whole just 6 tokens idea. Despite adding the SFE and DFI modules, their tests showed the inference speed, how many tokens the model processes per second, was almost identical to the original LLaVA 1.5.
That's huge. Better performance at basically the same speed. That makes it actually deployable.
Exactly. They managed to pack in more useful visual information without adding that dreaded computational overhead.
And this improved detail understanding should directly help with that frustrating CLEPA-P blindness problem we started with, right? The model getting confused by similar-looking things.
It does. You see it clearly in the hallucination benchmarks like PPOP and MBBP. Both the cropping and pooling versions of LLaVA-SP scored higher than LLaVA 1.5, meaning they were less likely to misidentify objects or describe things that weren't there.
Was there that example with Santa Claus and a snowman? That seemed like a perfect test case.
Oh, yeah, that one really illustrates the point. They showed LLaVA 1.5 2 images that looked somewhat similar. One was clearly Santa Claus, the other a snowman. LLaVA 1.5 got confused. It called both of them a snowman. It completely missed the specific details, the red suit, the hat shape, the things that make Santa Santa.
I just saw a white, roundish figure.
Pretty much, yeah. It relied on the general global features, but both LLaVA-SP models, they correctly identified Santa Claus.
Because the SFE and DFI help them focus on those distinguishing local details?
Exactly. That improved ability to see and differentiate fine-grained regional features made all the difference.
Okay, so mostly positive results.
Yeah.
But digging into the paper, there was a nuance, right? Something about the Detail Feature Integrator, the DFI, maybe not always helping the pooling version.
Yes, and it's good that they included this. It shows careful analysis. While the DFI consistently boosted the performance of the detail-focused cropping model,
Mm-hmm.
it sometimes actually hurt the performance of the global focus pooling model on certain tasks.
That seems counterintuitive. Why would adding more fine-grained detail integration harm a model?
The researchers hypothesized it's linked to the pooling operation itself. Remember, pooling averages things out. It abstracts and smooths the features to get that global view.
Right, it blurs the details a bit.
Exactly. So when the DFI's cross-attention mechanism then tries to look back at these already averaged features to integrate detail, it struggles. It doesn't have clear, sharp points to focus on.
It's like trying to add footnotes to a blurry summary.
That's a great way to put it. The attention mechanism can get confused and might even over-focus on unimportant artifacts or noise that remain after pooling. They even showed this with attention maps on a noise image. The pooling plus DFI model was putting strong attention on meaningless spots.
Fascinating. So the abstraction that helps pooling globally can interfere with the detail integration step locally. It really shows how these components interact in complex ways.
Definitely. It's not just about adding more layers, it's about how they work together.
One last thing on the method itself, its versatility. This isn't just a fix for a lobby, is it? They showed it works more broadly.
Yes, that's a key strength. They tested the LLaVA-SP approach, the SFE and DFI, as an add-on module to other MLLMs that use completely different vision encoders.
Like which ones?
They specifically showed improvements with CICLIP L16 and Intern VT 300 EMMA. It worked there too.
So it's like a general-purpose visual enhancement plugin you could potentially add to various models.
Exactly. It confirms the strength of the architectural idea itself, independent of the specific LLaVA framework.
Okay, let's wrap this up. LLaVA-SP seems to have really cracked a tough problem. Getting MLLMs to see finer details and understand spatial relationships much better. But crucially, doing it without the massive compute cost by cleverly using just 6 specialized tokens and that SFAD5 projector. Efficiency meets performance.
It's a genuinely elegant solution, and what's really exciting to think about now is, well, what happens next? All these experiments were done mostly on 7 billion parameter models like Vicuna 1.5.
Which are powerful, but not the top end anymore.
Right. So the big question for you, the user, and for the field is, how much more powerful does this LLaVA-SP enhancement become when you plug it into the really huge models we're seeing now? The Quen 2.5s, the Mistrals, the Lam A3s, models with much deeper reasoning ability.
Combining that reasoning power with truly detailed visual perception,
Yeah.
that could be a game changer.
It really could. And the researchers themselves point to one final area for refinement.
Which is?
While the inference cost is low because of the 6 tokens, the SFE component itself, using those convolutional kernels, currently has a fairly large number of parameters. It makes the projector module a bit bulky.
So the model file itself is bigger, even if it runs fast.
Exactly. So future work will likely focus on making those convolutional parts more parameter efficient, maybe using newer lightweight convolution techniques without losing the performance gains. That would make the whole thing even leaner and more efficient from start to finish.
So even better detail, still fast, and maybe even smaller models down the line. Very cool stuff.